All right, good morning. So, another question from NCERT Semiconductor Devices. I find students struggling in semiconductors, and therefore my current focus is semiconductors. So, this question is on a photodiode, okay? And the question is, if we bombard the semiconductor PN photodiode with a wavelength of 6,000 nanometer, and the band gap, if you see, is given to be 2.8 electron volts, which is pretty big, if you compare this with silicon. Will we be able to detect this wavelength or not? So I hope you know the principle of photodiode working. Briefly, I will tell you what happens in a photodiode. So what happens in a photodiode is this, and understand it from diagram perspective. It's very interesting to, understand a photodiode. So I'll just draw a sample photodiode, and you have this photodiode being drawn by me, and you can just notice what happens. Okay, I will not get into the construction detail, but we will just keep it to the concept. Okay, so after some time there is a diffusion layer that gets created having immobile ions on both the sides, right? So that is natural diffusion current that flows, and on one side, which is your P side, where you have a lot of holes, boron, for example, right? Borons. And so you have this boron impurity, and then on the right hand side, you have the N type semiconductor because it is given it's a PM photodiode. So on the right hand side, what we will do is we will draw the N side of it. And okay, I'll just draw this quickly so that we can concentrate on the main topic. So that's your P side, and you have N side, right? And a lot of electrons, from N side went towards this side, and there was a depletion layer which got created. This is your depletion layer, and now what you have here is a lot of negative ions on this side. These are immobile negative ions. Okay, and you have positive ions. These are phosphorus, for example, pentavalent. So these are pentavalent, but they have lost the extra electron, so they are positive now. So this is now, for example, P4 plus, and this is a phosphorus 5 plus, right? So you have ions. In a photodiode, what happens is, and just for your knowledge, a photodiode, when you make it work, please do not have any bias on it. Please do not, you know, forward bias it or reverse bias it. Do not do anything with it, right? Keep it at a zero bias level. Don't touch it at all. Just keep it the way it is, like you can see. And when, the way this operates is when the photons come here, and the photons carry an energy of h nu, and this is hc by lambda, right? What happens is you have an energy you can calculate. So, for example, this is the wavelength you're referring to. So, h into c divided by 6,000 into 10 raised to power minus 9 meters, right? So, we will put the values of Planck's constant and electricity. So, this is the energy being referred to, which is the energy of the wavelength, the photon, right? So, this is the energy of the photon which is striking. Now, what happens is the band gap is the band gap, right? So you have this concept of, I'm drawing a very simplistic view of the band gap and stuff like that, as you see in silicon and the germanium, right? So you can see that the band gap is available to you here, right? So this is your valence band, this is your forbidden energy gap, which is the band gap. So this is 2.8, and then you have the conduction band, and you want that the electrons which are in the valence band, right, they jump to the conduction band to participate and leave behind holes. Very simplest picture. Now, for a photodiode, the phenomena is that the photons have to strike the depletion. So in a photodiode, in a photodiode, in a photodiode, right? The photons which are coming, okay, these photons with energy h nu, which we just calculated. In a photodiode, the photons must strike the depletion region. Okay, so they strike the depletion region. So they don't strike, they do strike all the regions, but the beauty of the depletion region is if you strike the depletion region and you're able to create a electron hole pair, okay, because you are sending the photons and this negatively charged ion or a positively charged phosphor. So this is your boron, right? Boron is getting negatively charged and it lost the hole and it got depleted in the depletion region. And this pair, when this gets created inside the depletion layer, so an electron is released from the phosphorus ion, and a hole is released. It gets created. What happens is the hole automatically, and there is an electric field here, right? So there is an electric field here, right? So once you have an electric field also here, which is from the positive to negative, automatically what happens is the holes which are positive, right, they start moving towards this direction, right? So the holes move in this direction and the electron starts moving in this direction. So this electron and this hole I'm referring to has got created, this pair got created inside the depletion region, okay? And this got created because inside the depletion region you have a immobile ions of phosphorus and boron. Boron ions and phosphorus ions are inside, they have nothing except that they're like ions, right? So they have their plus and a minus, and when the photon strikes them, it releases an electron, one more electron, and leaves behind a pair, leaves behind a hole. So what are we trying to say is that the creation of electron hole pair is inside the depletion layer, okay, depletion layer. And I told you the current, the electrons move in this direction because of the electrostatic field inside the depletion layer, and the holes, they start moving in the opposite direction. So the net is that you have a current which is flowing in this direction. And if you close this circuit and you put a small micro or a milliammeter, like this, now what happens is this will see a photocurrent. Okay, so this will see a photocurrent, right? Which is only possible if the energy you supplied, which is this is the energy you supplied, so this is a supply, is able to overcome the band gap, right? So the EG, whatever energy you supply, H nu, which we have just calculated, that has to be bigger than the band gap of 2.8 electron volts, which is, if I were to convert it into joules, into 1.6 into 10 raised to power minus 19 joule, okay? This is the condition. The energy of the photon should be greater than the energy of the forbidden gap, right? So this is what you need to do. So what is that you're left with is, let's calculate the value of hc by 6000. Let us see how many joules of energy this is. If this energy turns out to be bigger than the band gap, you will see a photocurrent which is flowing in the external circuit where you see this ammeter. It will show you some fluctuation. Let this E is equal to H into C by 6,000 into 10 raised to power minus 9 joules, right? And then we will compare it to this value and find whether you will be able to detect any current here, right? So this will decide the fate of our answer. If you see the values of H and the values of C, H, C is given in the CBSE question paper. So these are always available even in JEE and NEET examination. You really don't need to memorize this. Just start putting the values of H and C. So a quick calculation will tell you that this is around 0.21 electron volts. And you can see the band gap is 2.8 electron volts, right? So 2.8 electron volt is your band gap, right? So what it means is that the energy you supplied using the photons is less than the band gap. I hope this made sense, right? So you will not see any photocurrent. So no photocurrent will be visible. No photocurrent will be visible, right? Right. So the answer is no. If you look into the question which NCERT, so can it detect? The answer is no, it cannot. So